Today we're going to be talking about deep learning on AWS with NVIDIA. We're going to try and take you through the entire pipeline today from training all the way to deployment. So along with me, my name is Eddie. I have Jahong. We're both solution architects at NVIDIA. And basically our job is to help our customers, namely Amazon and AWS, use our software, use our hardware more effectively and efficiently. So this is kind of what we want to talk about today. So we're going to start off the relationship that NVIDIA and AWS has, how we work together from a software perspective, from a hardware perspective, and how we put all that together. And then we're going to talk about the AI landscape that we provide to AWS for all of the customers to use. And then we're going to dive a little bit deeper into the training and the inference and deployment stages of that entire pipeline. So first off, I always like to show this as kind of the overall flow of what NVIDIA offers. So all the way at the bottom, most people are familiar with NVIDIA because of the GPUs that we have. So a lot of you are probably gamers. You're probably familiar with a lot of our gaming GPUs. But we also have a lot of the higher end A100s or H100s in the cloud or in a data center. On the other end, we also have edge GPUs, which we call Jetson. And all of these solutions are kind of integrated into AWS or Amazon solutions today. On top of that, we have what we call NVIDIA AI Enterprise. And basically what that is kind of a whole host of software and containers and a lot of other things that allow you to easily develop your solution. And then on top of that, we have application workflows. So things like Clara for medical imaging or Merlin for recommendation systems, NeMo for conversational AI, and so on. So a couple of these we're going to hit on a little bit later. So first I want to talk about the relationship between NVIDIA and AWS. So there's a lot of things that go on. Here's some of the, I guess, maybe the top 4 things that we kind of do together. So the first one is machine learning. So I would say a big portion of this conference is machine learning or deep learning or something related to that. So we kind of partner together to kind of bring the best solution, whether it's hardware or software or a combination of that all together. The next one is virtual workstations. And if you have, say, an entire group of people that needs to do graphic design or something like that, but you don't want to buy each one of them a workstation, a really easy way to do that is a virtual workstation in the cloud with AWS. And we also have things for high performance computing and Internet of Things at the edge as well. And here's a few of the offerings that we kind of paired together with AWS. So the first 3 on the left are going to be hardware offerings. So if you're familiar with AWS instances, you're probably seeing things like the P4D or the G5 or the G5G. All of these are powered by NVIDIA GPUs. And they're for different things. So for example, the P4D and P4DE are for things like large-scale machine learning training, whereas the G5 and G5G are more for graphics-intensive applications. Then we also have software integrations. So a lot of you are probably familiar with Amazon SageMaker. If you actually deploy a model with that, you can use an NVIDIA Triton Inference server to deploy your model and gain all of the goodness that comes along with that. And then we also partner on the edge, as I mentioned before. So AWS Panorama and Lookout for Vision are powered by NVIDIA Jetson. And the last thing here is NVIDIA GPU optimized software. That I'll actually come back to in just a second. So I think out of all of the technical material that we'll go through today, even though this is not the most technical slide, this is probably one of the most important slides. NGC is basically the way that you as a customer or you can help your customers get the most optimized software. So what this is basically a repository that contains containers, optimized models, Helm charts, ways to deploy your model in SageMaker, different things like that. But one of the most important pieces here is every single month, we actually put out containers with all of the optimizations that we have. So for example, if you have a PyTorch code and you use one of our containers, 6 months later, you're going to use a newer updated container. Your code doesn't have to change, and you could actually get 2 or 3 times better performance on the same hardware. So that's one of the most important pieces of information I think we can get from this. And as I mentioned, we kind of work across the board, different different use cases. So from data science, we have things like Rapids, and Spark integration. For recommenders, we have Merlin. Today, we're going to kind of focus on the right side. So for speech and vision, we're going to talk about what we call TAO. And then Jahong is going to talk about inference later with Triton. And I'm going to talk a little bit about large language models with what we call NeMo Megatron. But before we do that, I wanted to kind of highlight some of the hardware and hardware features that we have. So these are the things that you want to utilize as much as possible when you're using these software SDKs. So the first one is the NVIDIA A100. And this is what is actually what you're using whenever you're using a P4D or P4D instance. So whenever you start one of those, look at the GPUs, this is actually what you're looking at. So there's 40 gigabyte and 80 gigabyte versions of that. And the reason I mention that is because as models and data sets get really large, you actually want more GPU memory, because whenever you try and pack all of that information into a GPU, once you scale past a GPU or to a different node, you're actually losing performance. So the more you can pack into a single GPU, the better. So there's also tensor cores in these. So we announced these a few years ago, but we've kind of built on them. So this is the 3rd generation tensor core. And basically what happens is if you're running a deep learning model, this is actually going to speed up the matrix multiply and accumulates that are happening inside those operations. And then this is our new GPU, the NVIDIA H100. So this is actually coming to AWS soon. I don't have the name of the instance yet for you. Maybe you can talk to AWS to figure that one out. But so the things I want to highlight here is the next generation NVLink. So this is actually going to give you a connection between GPUs of 900 gigabytes per second. So this is really, really quick when you're trying to transfer things like model weights or data between different GPUs. There's also 2nd generation MIG. What that is multi-instance GPU. And that allows you to actually split up the GPU for different tasks or for different operations. So you could have part of the GPU doing inference while the other part is training. One of the important pieces here that I wanted to highlight a little bit later is the transformer engine, but keep that in mind for a slide from now. And just a few performance numbers of what it looks like compared to the A100, the previous generation. So on the far left, you can see that this is training a large language model, so anywhere from 70 billion parameters all the way up to 1 trillion parameters. And on those large scales, you can actually see from 4,000 A100s to 4,000 H100s, it takes a month to a week. So significant speed up just by using the newer hardware on that. And on the right side, you can see similar things for inference. So using 10 DGX systems, which is the equivalent of 80 GPUs. You can get 10 concurrent users on that using a 530 billion parameter model. But on the H100, you can actually have 300 concurrent users. And coming back to this is one of the more important features of the H100. So the transformer engine is actually purpose-built for things like natural language processing models like BERT or large language models like GPT or T5. And basically what it does is while you're training your model, it's doing kind of stochastic understanding of what's happening. And instead of converting your model to 16-bit, it's actually converting your model to 8-bit. And it does that in a way that you don't lose accuracy whenever you're training. And whenever we train this on large models, say 175 billion or 530 billion, we actually see a 6 times faster training time just by using this transformer engine. And lastly, before I move on to the software, these are kind of what I mentioned before, the different instance types that you can get with GPUs. So the top 2, the G5G and G5, are more for graphics intensive applications. The middle 2, the P4D, P4DE, and P3, are more for machine learning training, HPC type things. And then the G4, which is powered by the NVIDIA T4, is more of a universal type instance, and you can use that for machine learning inference, for training, for transcoding, for anything like that. So that was kind of a short trip through the hardware. So I want to move on to kind of the meat of what we want to talk about today, which is the software stacks that run on top of all of that hardware. So first I want to talk about computer vision and conversational AI. So If we focus on computer vision for now, there's so many use cases for computer vision that it's really hard to count. So if you think of just healthcare or retail, there's probably hundreds that you can just write down for either one of those. And the problem with it is each one of those is slightly different. So you have to develop an entire pipeline for data preprocessing or training your model or deploying that model completely differently for each one of those. And what that kind of looks like is building a pipeline like this. So first, you have to do some sort of data labeling or annotating and preprocessing that so that you can actually use it with your model. And then you actually have to train the model. And that's not as easy as it sounds. You can't just hit the go button most of the time and have it train. You have to do hyperparameter optimization. You have to do other kind of tuning to make your training not only fast, but also converge properly. And then after that, arguably, a third more difficult thing is to actually deploy that model and making it optimal and being able to serve your customers or your users with that. So what I want to talk about today is kind of the middle piece of that, the training piece. So what we have is called NVIDIA TAO Toolkit. It stands for Train, Adapt, and Optimize. And basically the workflow is you take some sort of pre-trained model, you run it through this toolkit, and you get your optimized model out that you can then deploy. The way that we've thought about it is actually part of that NGC that I mentioned before. We have a bunch of pre-trained models that you can start with there, or you can actually bring your own model. So if you have an Onyx model or a TensorFlow model or a PyTorch model, you bring that and use this toolkit to kind of prune your model or retrain your model on your own data set. And that's kind of what this TAO toolkit piece does. So not only does it train, but you can also prune your model, which I'll talk about a little bit later. And it also does training-aware quantization. So all of these things that help you optimize the training process are already built into this framework. And then I won't spend too much time on this. This is the deployment piece. I'm going to hold off for Jahong to cover that. So here's some of the benefits of using TAO Toolkit. So it's really, really easy to use. So instead of building an entire PyTorch code base, basically all you have to do is something like TAO train and give it parameters, and basically everything else is done under the hood for you. It's also built on top of TensorFlow and PyTorch, so it kind of abstracts away all the hardness or the complexity of that. So if you're a new user or you just want something done quickly, this is a good way to go. And it's also supported by a lot of our experts. So we have entire engineering teams and also support engineers that work through this. So if you have problems, you can contact NVIDIA support or the forums, and they actually go through and help you with this. And then how can we use it? So you can actually grab the container from NGC and run it on EC2. Or you could, if you want to use Amazon SageMaker, you could use the bring your own container model, either way. So just grab the TAO Toolkit container, drop it on whatever AWS instance you have, and go from there. Here's just a kind of a list of some of the vision models that we have as part of the pre-trained models. Obviously, this isn't all of them, and if what you're looking for isn't covered here, definitely take a look at the entire list that we have there. So some of the things that we have are like people detection, traffic camnet, which actually does route planning and some stuff like that, some pose estimation, some facial landmarks and things like that. And one of the important pieces here is to notice that these are state-of-the-art models. So these have been trained to 85, 90, 95% accuracy so that whenever you grab them, you know that they're actually going to perform for your task. And I would be remiss without kind of noticing the second part of this. TAO also uses kind of the same mechanisms for conversational AI. So you can kind of use the same workflow if you want to do speech recognition or natural language processing. So we have pre-trained models for all of those as well, and the same TAO toolkit will work with the same kind of workflow to train your model. So this is what the TAO stack looks like. I think any NVIDIA presentation that you go to will have something similar to this because every piece of software that we have is built on top of the hardware and then on top of our CUDA-X, which is basically all of the acceleration libraries that we have. Then the SDK is sitting on top. But one of the things that I wanted to point out here is everything that's inside the TAO toolkit is kind of containerized in Jupyter notebooks. So it's very easy to get started. Anything from data prep to data augmentation to training to pruning to deployment, all of that is encapsulated into Jupyter Notebooks for being easier to get started. Now, just a few interesting features that I wanted to go through. So I mentioned model pruning a couple of times, and this is really important actually whenever you're talking about optimizing your training process. So if we take this example, we can see that one of the neurons in one of the layers is actually being taken out, but obviously it's a lot more complex than this. You're not gonna typically train a 6-neuron neural network. Typically it's a lot bigger than this. But what's happening here is we're looking for specific neurons or specific layers, specific tensors that are actually not activating to make the output different. So whenever we see that, we can actually take those out and not make any impact to the output. And we can actually see an up to 8 times model size reduction for that. And kind of along with that, we also have quantization. So inside the TAO toolkit, there's post-training quantization, which is basically you take your trained model and then you run quantization after it to convert all of your weights to end 8. There's also quantization-aware training, which while you're doing back propagation and forward propagation, it actually converts to end 8 while you're training so that it actually understands what it's supposed to learn before you actually do the quantization later. And 2 more features that I wanted to quickly mention. One is automatic mixed precision. So this is something that kind of comes in most frameworks now. So if you're using PyTorch or TensorFlow or anything like that, if you turn on the automatic mixed precision flag, most likely, most of your operations are going to be running FP16 on the GPU. And the benefit of that is when you're converting from FP32 to FP16, you're actually making the model smaller. The inference time or the forward pass is going to be quicker. And then the last thing is data augmentation. So there's rotations, there's crops, there's brightening that you can actually do inside the TAO toolkit if that's something that you needed to do in your entire workflow. And so the way that TAO toolkit works is it's kind of a low-code solution. So basically you would take these configuration files and set what you need. So things like the backbone network that you want to use, the size of the network that you want to use, the paths of the pre-trained model, all of the configuration that you need. So you can start with a different learning rate and try your training. You can start with a different weight decay. All of those things can be done inside of the configuration file and then it's taken care of in the back end for you. So what we can do with that is actually take something like one of our pre-trained models, like this PeopleNet model, which basically does people detection. And if we want to transfer that to work on infrared images, we can actually use TAO toolkit with the pre-trained model, give it a data set, and kind of fine-tune on that. And what we get out is actually a data set that can detect people inside of those infrared images. And another helpful use case that I found is actually adding new classes. So here we're actually using a PeopleNet model, but instead of just detecting the people, we actually want to, I guess, detect the helmets as well. So think about a construction use case or something that you want to make sure that everyone's wearing their helmet properly. So you could actually take a labeled data set here and train and just add another class to your network rather than fine-tuning the entire network again. So here's a couple of resources. The links, I believe, will be shared later, but the gist here is at developer.nvidia.com. All of this stuff can be found if you just search for TAO toolkit. You can go to the white page, or the white paper, the product page, all of that stuff is already there. And then there's a lot of resources as well that are pointed to by those pages that are blog posts and GTC talks and other things that are really helpful. So, switching gears one more time. So we talked about computer vision and conversational AI. So now we want to kind of scale that up. And one of the biggest use cases that we have now is large language models. And there's so many use cases coming out now, so many startups, so many big companies that are actually working on different types of large language models. So from GPT-3 for text generation to things like DALL-E for image generation. All the way out to like Mega Molbart for life sciences and understanding molecular structures and things like that. All of these things can utilize techniques that large language models have brought to the table. And this is kind of a cool slide that I like to show. The number of research papers that are actually published per year has been kind of exponentially increasing when we look at just transformer and large language models. So for transformer and BERT, there was definitely a lot of them, but it was kind of the entering into the field. But once we've gotten past GPT-3, things have kind of exploded, and the number of papers when we see something like DALL-E is just exploding. So one thing that I like to mention whenever I'm talking about large language models is it's not always useful to train a large language model. You have to know when to use it. And there's some requirements that I like to go through. So the first one is, what kind of data do you have? If you have labeled data, and it's not that big of a data set, then maybe you want to use traditional techniques for training that, where you have your sequences, you have your labels, and you just train like you would any other neural net. But if you have a large corpus of data, like say Wikipedia or something like that you want to train on, maybe you don't want to go through the entire Wikipedia data set and label everything. So that's what these large language model and training techniques are for. Also, depending on the model size that you want to train is kind of the difference in the regular NLP approach and the large language model approach. So if you want to train, say, a 100 million parameter model, maybe you don't want to use all of the techniques to split your model across GPUs and all of that, because it's not going to be worth it. But if you're training a 1 trillion parameter model, you need all these techniques, or your training is just going to be so astronomically slow that you're never going to get a result. One more thing is what the desired capability of your model is. So a couple of years ago when we were training BERT, it was for one specific task. It was for classification, or it was for text generation or something like that. But now, with things like GPT-3, T5, DALL-E, all of these, they're trained much more generally so that you can kind of prompt tune or tune on top of it very easily, and they're built for much more general use cases. So I'm not going to go through all of the points here, but I want to make the point that training and deploying large language models is really not for the faint of heart. It's really, really difficult. The reason I show this is because a little bit later I'm going to show you what we've done to kind of alleviate some of these. But some of the biggest ones that I want to point out are things like finding optimal hyperparameters or converging your model. If you train a 530 billion parameter model, it's going to, if you don't have thousands and thousands of nodes, it's going to take years to train that model. And if you get to the end and it doesn't converge, what do? You have to start over again. So being able to know that your model is going to converge, know that it's going to converge to a place where you can actually use it, all of these things are kind of things that we have to think about when we're training large language models. So at NVIDIA, what we have is what we call NeMo Megatron. So this is kind of our solution for training large language models. So again, it's built on top of all of the NVIDIA hardware. So at the bottom, you can see AWS. We also have DGX SuperPod, which is there, which is basically a big cluster of machines, and DGX Foundry, which is kind of the same thing. And then the green bars on top is actually what NVIDIA NeMo Megatron kind of provides for you. So all of it is containerized, kind of like the TAO toolkit that we mentioned before. It gives you distributed data preprocessing, so instead of just doing preprocessing on one node, you can actually do it across an entire cluster now. Hyperparameter tuning, which I think is one of the biggest pieces here, and then distributed training and accelerated inference. And one of the pieces that I wanted to mention too is the very top is convergence recipes. So if you go to train, say, a 175 billion parameter model, you want to know where to start from. You don't want to just guess at hyperparameters and see what works. So what we've put along with all of the things in this container are verified recipes that we know will converge, so you can just use your data with the verified recipes and train your model. So like I mentioned, one of the most important features, I think, of NeMo Megatron is the hyperparameter tool. So basically, this will give you the opportunity to say, I have this many nodes, I have this much time, what size model can I train? Or I have this model, I have this many nodes, how long is that going to take to train? So any combination of these three, and it can kind of give you the other estimate of the other one. What this also does is find you the most optimal recipe for that. So say you want to train a 50 billion parameter model, you don't know what type of hyperparameters, like how you should split your model across different GPUs. It actually does that for you and tries to find the most optimal path for you to train that model. And there's also data curation and preprocessing, so things like data filtering or deduplication, all of that can be done inside of NeMo Megatron, so if you need to do that with your data set, you can do that here. And then these are a few of the optimization techniques that we use that are built into NeMo Megatron. So if you're familiar with large language models, you've probably seen a few of these before. So pipeline and tensor parallelism are basically a way to split your model across GPUs. So if you think about a regular BERT model, it's small enough to fit on a single GPU, so you don't have to do any of these techniques. But if you train a 50 billion parameter model, that's not going to fit on a single GPU, or even maybe on a single system with the amount of data that you need to train that. So you have to use these techniques to split your model up properly so that you can actually train that. And here are just two of the other kind of state-of-the-art techniques that we've introduced into NeMo Megatron. So one is sequence parallelism, and basically instead of splitting your model across the tensor dimension or the data dimension, we're actually splitting it across the sequence dimension. So there's a lot of ways to split your model so that you can actually either get better performance or lower memory consumption or kind of different optimizations for whatever your task is. And then selective activation recomputation is one of the last ones. And basically what this does is while you're doing your forward pass, instead of saving all of those activations, it's going to recompute some of them whenever we're doing the backwards pass. And we've actually found that that not only lowers the memory footprint, but can actually speed things up because computing sometimes is a little bit faster than going to do a lookup somewhere. So here's some of the results. I just wanted to point out a few of them. These are a little bit outdated, I believe, but still kind of get the point across. So if you look at the green box kind of near where it says 175 billion, it says 43. So what that represents is how long it takes to train a 175 billion parameter model. And that's in days. So that's 1.5 months that it actually takes to train one of these models on 800 GPUs. So this kind of comes back to what I was mentioning before, is it's not really for the faint of heart. If you don't really have a good understanding, it could actually hurt you to try and train one of these kind of from scratch. And like I mentioned before, I wanted to come back to this slide. So this is all of the points that I mentioned before. And then on the right side, this is how NeMo Megatron is actually helping all of these. So for something like the optimal hyperparameters, we have the hyperparameter tool. Or the convergence of the models, we have things like the verified recipes for GPT and T5 models that you can start with your data set. One of the other things that I wanted to point out here is scaling on clouds. So if you're working with AWS, we actually have recipes and scripts that show you how to spin up an entire cluster for AWS or on AWS, and then drop our container on it and go with training or inference or whatever you need. And this is one of my last slides. So this is kind of to wrap up what we have with NeMo Megatron. So it's an end-to-end solution for bringing your own data and training these large language models, whether you need data curation or pre-processing or just going straight to training with one of these large language models. Also, some of the state-of-the-art techniques. So one thing I didn't mention is we also have something called Megatron LM. So this is kind of research at this point. So our research team works on that, and all of the features that they develop are then put into NeMo Megatron for our enterprise customers to use. So anything that our research team points out as something that gives them some sort of speed up or some sort of performance enhancement goes into NeMo Megatron as well. And one last thing is it's easier to use just because it's containerized, just like the TAO toolkit was before. So again, here's some resources. I think these slides are going to be shared. But I think that's all the content that I have, so I'm going to hand off to Jahong to talk about deployment and inference.
So once you're training these models, how do you actually bring it into production to actually give you business benefits? So this is where the deployment comes in. So you want to deploy your models and in an optimized way in order to give you the best business gains possible. So in NVIDIA, we are providing a two-step solutions. So first of all, after every model is trained, it's providing you good accuracy in inference, but it might not be optimized for speed. So in actual deployment, you might have different constraints. For example, you might want to reduce the latency or increase the throughput somehow. So there are some technique we are going to talk about, how you can apply these optimizations to the model itself. And then after the model has been optimized, you will use an inference server to bring it into actual production, to scale it out based on your business needs. So in NVIDIA, there's actually also a lot of challenges in AI inferencing. In here, we are listing 6 vectors of it. The first is that you might have different models for different kind of use cases. For example, CNN are very good at doing computer vision workload. And then for different language models, there's transformer-based models and a bunch of other models for specific use case as well. And as we just talked about, for different apps, there are different constraints. For real-time inferencing, you might want to optimize for the latency. And then for offline scenario, you might want to do batch inference to optimize for the throughput. And then also, there are still some streaming use case that require some specific functionality in your model or your inference server. And then another very common phenomenon we are observing is that a different use case, different models might be using different frameworks. For example, some are very familiar with TensorFlow, some are very familiar with PyTorch, some may choose others. But in one single thing, if you're using multiple different inference server, these frameworks, you might very likely have very different inference server as well. So how can you have a unified solution to do all of this inference together? So that's where we introduced the Triton inference server. So, and before that, there's also the model optimization, TensorRT, I've talked about. So TensorRT is basically a world-leading inference performance framework. So it's both compiler that's going to optimize your model during the compilation time, and also it's a runtime inference library that's going to provide you speed-of-light inferencing in actual deployment. So in this slides, we are showcasing some of the most common use case we see customers are using TensorRT with. So as we can see, for computer vision workload, we're seeing up to 36x speed up compared to CPU. And then for speech recognition, we are seeing almost 600x. And of course, there are some others we are not listed in this slides, but actually we've seen customers using TensorRT all over the industry. So what is actually happening inside TensorRT? So for this part, it might be a bit technical, but I hope all of this can convince you that TensorRT is the go-to solution when you want to optimize your model. So first of all, there's a reduced mixed precision. So unlike the training scenario, you might want to use the best precision in order to give you the best accuracy. But in inference time, time is more critical. And then a lot of times, you don't necessarily need FP32 precision, which is also known as the full precision, to meet your deployment needs. So that's where you can use TensorRT to optimize your model into half precision, for example, the FP60. And then if you want to go one step further, there's also int8 precision. But for int8 precision, you might be a bit careful, because you can see, going from the full to the int, there's actually 1/4 of the data that's being preserved. So in here, you might want to use a bunch of quantization technique in order to preserve your accuracy. And this will mean very different things for different kind of models. So you might be careful about that. The next step is called layer and tensor fusion. So if you are not in the model inference well, you might not be very familiar with this. But when you are running your models in GPUs, there's actually a bunch of different kernel calls that correspond to each operations. And then when this model are designed, they might not be designed to have the best inference performance. That's where you can apply this layer and tensor fusion technique to really fuse these very small kernels into a large one. And this will largely reduce your kernel launch overhead. And this is a very good technique we see on GPU. And in the plot here, as we are showing, this is actually a very standard QKV projection inside of transformer models. And then after the fusion, you will see very good speed up. There's actually a separate blog talking about how you can optimize your BERT model using TensorRT. That's a very good example of how this features works. And then aside from this, there's also kernel auto-tuning. So since each hardware is designed differently, there are actually hundreds of specialized kernels that's optimized for each GPU platform. And before you actually run your models on that specific GPU, you might not know which kernels works best for you. So that's why you want to use TensorRT. This optimizer will automatically run a bunch of profiling to help you select the best performing kernels for you. And in this way, we can ensure that you are getting the best performance on your deployment. The next one is called dynamic tensor memory. So unlike training, you might want to preserve all the intermediate results of your model inferencing in order to run the backpropagation or calculate the loss or everything. But in inferencing, you don't need all of that. You only need one final results. So that's why you can actually free those memory dynamically to really reduce your memory footprint. And you might not know what this means. So aside from the apparent memory reductions, you can actually easily run with a larger batch size on the same GPU. And based on a lot of customer feedback, this really increased their throughput by a ton. Okay, moving next, this is actually an optimization more specific to recurrent neural networks. So previously, when you run these recurrent neural networks on GPU, you need to run it one step by step. But TensorRT introduced this time fusion technique where you can fuse all those pointwise operations and GMS all together so that they can compute more efficiently. And then for the speed up, we are seeing about the speech recognition. If you recall, that's about 600x. That is what achievable by using this time fusion technique. Last but not least, we have a technique called multi-string concurrent execution. So when customers deploy their models, the model size might not be able to saturate the power of one single GPU. So in actual production, we are actually advising customers, if your models are too small, you can easily fit multiple copies of the same model in one single GPU. And in the case you are seeing here, that's a ResNet 50. And then a T4 is a very standard GPU you can get out of the G4 instance. You can actually fit 8 instances of this ResNet 50 and have them all run concurrently for you. So you can easily see that that means instant 8x speed up by simply doing so. So that's basically all the optimization that's happening in TensorRT. But of course, there's more to it, but these are the most general one, and we see most benefits from customers by leveraging all of them. And when you are actually running TensorRT, you don't have to specifically say turn this on or off. Actually, all of that are doing automatically for you. So all you have to do is run one, run too fast. All you have to do is basically one command line called TensorRT exec your model. And then today, if you want to experience about TensorRT, there are 3 ways we could recommend. The first is the native TensorRT, so you can directly go to the developer TensorRT page to experience it. But we are also integrating TensorRT with these frameworks natively. Keep skipping, sorry. So we have the Torch integration and TensorFlow integration. Both often are upstream. So if you can use it, you can just go to the PyTorch official documentation or TensorFlow official documentation. So with that, I'm going to switch gear into after the model being optimized, how are you going to bring into the model server? So NVIDIA Triton Inference Server is a solution we proposed to really help you deploy all models from all frameworks to meet all kinds of different use cases. So you can see here, we basically support any frameworks you are currently using that includes the very popular TensorFlow, PyTorch, and then the TensorRT we just talked about. And then we have optimizations for real-time batch streaming. And if your model deployment have a very complicated pipeline, we also provide this model example feature where we are going to talk about later. And then we can deploy this Triton Inference Server in any platform. So this might be a surprise to you, but Triton Inference Server is not optimized for GPU only. You can actually run it easily with CPU or any hardware as well. That includes the infrastructure that AWS provides. And then this also works on any operating system, and also cloud, local, and even embedded devices deployment. Another very important point to note is that Triton is also tightly integrated with DevOps and MLOps. So when you actually bring these models into production, one very important factor you will consider is how do you actually scale it? So that's what this feature enables to do. It's tightly integrated with Kubernetes, and then it's also integrated with the AWS SageMaker, if you are familiar with that. We have dedicated slides to talk about that as well. So last but not least, so having all this functionality ensure you have a universal solution for your model deployment. But what about the performance? So Triton actually provides a lot of building optimizations to help you get the best performance possible by utilizing your hardware to its fullest. And we are also going to talk about that later. So in this graph, we are showing the Triton's architecture. In the far left side, you can see we have different client libraries that's sending requests to the Triton Inference Server for standard to meet the business standard. So we're actually providing both Python and the C++ client library. And then we support both HTTP and gRPC protocol. So both are very standard protocol you are commonly seeing in all kinds of web applications. And then specifically for embedded systems, there's actually an in-process API that can help you to avoid this networking all at once. And then after this query reach into the Triton, there's actually where the first optimization happens. That's the dynamic batching. So I'm going to save it for later slides. But basically, after these optimizations, the models you are serving in Triton can execute your different queries based on its priority you set. So as you can see, we are capable of serving multiple models in one single Triton Inference Server. But in your real production, each model might mean different things for you. There are some with higher priority, some with less. So this functionality can enable you to really manage your model serving. And then in the meanwhile, we also provide a bunch of metrics, including the hardware utilization, and then the model throughput, and the latency, and so on, to help you monitor the model serving. And here is a comprehensive list of all the backend we natively support. Aside from all those we've talked about, one thing to be noted is that we also have NVIDIA-specific optimization framework for different kind of workload. For example, from the bottom part, we can see there's DALI for computer vision data preprocessing, NVTabular, specific design for tabular data, and huge CTR for rectangular system. And this is the first optimization we are going to talk about that really highlight the gen of Triton. So as we introduced, TensorRT has this concurrent model execution functionality, and it really aligns with what Triton is offering. So it makes it to work more seamlessly for you, and you can easily fit multiple copies or multiple models in one single GPU. And in here, as we are showing, there are three different ResNet, three ResNet models copies, and the 3 tiny Uno V3 copies, all run concurrently for you. The next one is the dynamic batching scheduler. So if you have never done inference on GPU, you might not know this. But if you have any experience, you will easily see that by simply increasing your batch size, you can instantly getting a much better throughput. And this is what this feature enables you to do. All of this batching are happening after the payload arrives at the Triton inference server. And then this dynamic batcher can wait for a specific time step to concatenate all these payloads into a larger one. And then after that, it will be executed with a larger batch size to ensure you're getting the best throughput possible. But one very good question is, how do you know how long I should wait for the dynamic batcher? Or what kind of batch size I should form? Or how many copies I was able to run in this specific GPU? So as you can easily tell, all of this are really down to what your model looks like and which GPU you are using. So that's why we introduced this tool called Model Analyzer. So after you give it the model artifact and telling it some of your QoS constraints, this model analyzer will run a bunch of profiling with different kind of configurations and automatically generate a graph as shown on the right to tell you what's the best 3 performing configurations for your model. And in this way, you can really choose which one will be working best for you. So there's also one additional backend I really want to highlight. So Eddie has talked about NeMo Megatron, to how to train your large language models. But what can you do to bring into production, right? So it's so large, it's not going to fit into one single GPU, maybe not even one single system. So that's why we introduced this fast transformer backend that's specially designed to serve this kind of large language models. And as you can see, we also provide the pipeline parallelism and tensor parallelism in order to fit it in a multi-GPU or even multi-node setup. And all of these are currently in early access, so if you're interested, feel free to reach out. We are definitely happy to share more details. Moving next, we have this very important feature called model pipelines with business logic scripting. So as we mentioned, in actual production, pipeline is very important. And it's for different kind of business needs, you might need very complicated logics to be embedded into your model deployment. And by using this business logic scripting, you can actually design your code using Python or C++ and insert all these complicated logics inside it. Another very important feature is called decoupled models. This is commonly seen in automatic speech recognition. So as you can see, when you are running a very long sequence to do this automatic speech recognition, you might not want to wait until the whole sentence being generated for you, right? You might want to just have a token, output it token by token for you, just to save your time. Otherwise, you might be seeing very, very long wait time that may be a few seconds or even up to minutes. This will really be a very best thing for your customers. So that's why you might want to use this decoupled models features, so you don't have to strictly have a one-on-one mapping of your payload and then the output. You can actually do whatever you want. You can have multiple payload corresponding to one output, or one payload corresponding to multiple output. So I hope all of these features are appealing to you, but just to convince you that this is really production ready and all of our customers are really using it in actual production. This is a short list of all the customers that's currently using Triton in their actual production. So if you search any of these things with Triton, you will likely see a blog, an announcement, or even a talk that go in depth with how they are leveraging Triton and TensorRT in their actual productions. And one thing I would really want to highlight is this real-time spell checking for the product search on Amazon.com. So this is one of the great achievement we've done with the Amazon search team together, and they're actually going to have a dedicated talk about that as well. So if you guys interested, keep an eye out and look for one of the search talk in this re:Invent. So if you would like to learn more about Triton and TensorRT, here are some of the resources you can check out. But last but not least, this is the part I'm saving for the SageMaker. So if you don't know it already, Triton is actually already integrated with SageMaker. So in this way, you can actually experience both benefits of Triton and SageMaker. So using SageMaker, you can see it's really cost efficient and it's already ML ops ready. So you can easily design what kind of scaling policy you want to use with SageMaker. And then it's quite flexible since SageMaker provides all kind of different endpoints for real-time scenario, for offline scenario, or even batch scenario. And also SageMaker are doing all of the security checks for you, so you can configure the VPC and the fine-grained IAM permissions as well. And one additional thing is that SageMaker really help you do most of the heavy lifting, so you don't have too much to worry about. So if you want to get started with Triton Inference Server on SageMaker, here are some additional links and resources. And it's actually already part of the official documentation of SageMaker. So if you go to the developer guide of SageMaker and search for Triton, you can easily see how you can serve your model with it. And here are some additional blogs we've been publishing together. This also highlights how many customers are experienced with it and how much more works we are doing together. And also, Vikram from the SageMaker team is actually announcing a new feature called multi-model endpoint with Triton on SageMaker. So if your workload contains multiple different models and you want to use it on SageMaker today, check out that session on Friday. Okay, with that, that's basically all of the content. So we are going to just conclude a bit and do a call to action here. So in this presentation, Eddie talks about NVIDIA GPUs, how it powers the most compute-intensive workloads, from computer vision to speech, language, and so much more. So, and if you are using computer vision use case or speech use case, then you got to try out this TAO toolkit, which is automating the whole process for you. And then we also offer the NeMo Megatron, which is an open source toolkit for large language models. So if you're experimenting with it, or even if you're just starting to consider it, definitely check it out. It has all kinds of documentations and best practice for you to really save your cost and save you a lot of experiment cycles. And then coming to the inference side, we have the TensorRT, which will optimize the model itself, and then Triton Inference Server to really simplify your deployment of the productions. With that, we are going to also call out that NVIDIA provides these Inception programs. So if you're interested, feel free to scan this QR code and check out this link for more details. And one last thing, we actually have a NVIDIA AWS AI/ML Accelerated Inference Meetup. So this will cover more about Triton, TensorRT, and how it works on SageMaker. This will be happening on a Wednesday. So if you guys are interested, feel free to come up and take a scan or just note it down. We will be expecting you there. With that, we finally go over all the presentations. And if you guys have any questions, we can take it from now.